Section 7.2 is all about volume, although I split it into two distinct sections. We learned about disk and washer method already. Those are volumes of revolution, where the shape is whirling around an axis, whether it be the x-axis, y-axis, some other line. Cross sections is what we're going to be doing now. And cross sections, you're not rotating the shape. The shape is already three-dimensional. These are really tough to draw, but I found a really cool illustrator on the internet, and using Geographa, we can kind of see it. So I'm going to go there right now. Okay, you can pick a common shape. There's squares. This happens to have semicircles, equilateral triangles. Sometimes you'll see rectangles. Those are typically what College Board will use as well. I'll start off with squares. And you can see what happens as I take my cross-section through this region. It's a region that's bounded by the two curves. There's a red curve and a blue curve. Check this out. I think it'll be self-explanatory. Okay, here's the square starting at 0. As the curves get farther away from each other, the square has to get larger and taller. And as the curves come back and converge, the square gets smaller again until it disappears. Now you can add a whole bunch of different squares. And these are called cross sections. And together, if you have enough of them, the object starts to turn 3D. It's like a bunch of Post-it notes that all got paper mache'd together. Looks like an armadillo shell or something. And it eventually turns, as I said, three-dimensional. You can kind of see it's almost like a building forming with a cool-looking roof. But it's really just made up of a bunch of squares. Each cross-section is a square. You can see them now. One of the most famous architectural buildings in the world is the Sydney Opera House, and really it's made of cross sections. The cross sections aren't squares; they're a little bit more curvy, but it's kind of what this reminds me of a little bit. Let's flip over to semicircles. And again, you can see the same thing. The semicircles are the cross sections. If you put enough of them together, you get a 3D shape with a domed roof. Why should you care about something like that? Well, let's say that somebody engineered this building and you're in charge of HVAC, like my father-in-law, stands for heating, ventilation, and air conditioning. If you're going to cool this building or heat it in the winter, you need to know its volume. How do you find volumes? You use cross sections. Or maybe you want to paint it and use surface area. We're not going to go over surface area in our course, but that also uses cross sections. And finally, equilateral triangles, just for fun. Put them in as well. You can see that would be a little tougher, but equilateral triangles, the area to find those is a little bit more difficult. But you could start with just a few of them and build it up, and eventually it becomes a 3D shape. All right, so that's the gist behind cross sections. For me, the toughest part is reading a set of directions like this and trying to make an accurate picture, and hope that my drawing is sufficient and that I get it right. It says the base of the solid is the region bounded by the curve y equals, and there it is, negative x squared plus 5x minus 4. That's an upside down parabola. And the x-axis. Okay, so parabola crossing the x-axis, I have a picture of the region. I can see it in my mind. The cross sections to the x-axis. It should say the cross sections perpendicular to the x-axis. I left a word out. My apologies. Now let's put a perpendicular symbol in. Okay, I feel better about myself now. You have to say which axis you're perpendicular to. All right, find the volume of this solid. Well, the first thing I need to do is I need to graph the thing. I need to make a picture of it. And so I did that on my next slide. There's the area between the parabola and the x-axis, and I colored it a nice light blue color. In fact, it looks to me like it's a crystal blue lake. And I'm a bird flying above this lake. I'm flapping my wings and flying through the air, looking down at the lake, and I'm thinking about landing on it. I'm like, that looks so pleasant. But as I get closer to the lake, suddenly, out of nowhere, these giant pink squares come flying out of the lake straight up. all the way from 1 to 4. I only showed 3 of them, but they're everywhere. And it was terrifying, and I flapped my wings and flew away as fast as I could. But these squares ended up making a 3D object, kind of like you saw on Geographa, and I want to know its volume. Sorry for the weird story, that sort of helps people visualize. All right, find the volume of this solid. Again, I do have to say perpendicular to the x-axis, because if we turn all these squares 90 degrees, it does change the answer, believe it or not. It's a different building with a different need for air conditioning. It's not going to be the same answer. So the cross sections are perpendicular to the x-axis. All right, here's the deal. I grab one of these cross sections and pull it out and look at it. And if you think about this square, I can figure out how long this is by looking at the picture. This generic point that I'm putting an arrow towards is the point x comma y, but because it's on the parabola, it's actually x comma negative x squared plus 5x minus 4. And this lower point is x comma 0. I know it looks like it's right on the 3. That's just coincidental. It can be anywhere. Remember, there's a whole bunch of these different squares. So the length of this segment that I'm going back and forth on in black is just simply going to be top minus bottom. It's simply going to be negative x squared plus 5x minus 4. Now, because this is a square, the other side will be the same thing. This square represents a cross-section of the entire shape. All right, I'm going to move my square out of the way so I have some working room, but I still want to look at it. All right, the volume of the solid is simply going to be the interval. From 1 to 4, because that's where the square started and ended, of the area of one cross section. In this case, the area is going to be side squared, because that's what the area of a square is, dx. You think about it, area is two-dimensional. If you integrate something that's two-dimensional, you go up by a power and it makes it 3D. That's why this formula works. Now, please do not go ahead and square that out and do a 9-step FOIL, integrate all 9 parts. No. Grab your calculator, type this in, and get yourself an answer. And that answer will be 81/10 or 8.1 cubic units. All right, let's try something with a different shape. This time we have semicircles popping up. And I decided instead of having an upside down parabola, I'd have a bit of a sine curve. It's actually 3 radical sine of x, just to be more fun. That does go through the point 0, 0. It also goes through pi 0. That's why you see the pi there. Sine of pi is 0. And the cross sections, as you can see, are perpendicular to the x-axis. They're popping up as semicircles. Find the volume. Well, the first thing we need to do is we need to figure out how long this piece is right here. I'll just take a random semicircle. I'll happen to pick this one right here. This is the point x, 0. This is the point x comma 3 rad sine x. How long is that? Well, it's 3 rad sine x. All right, let's find the volume. We're going to integrate from 0 to pi. That's usually the easy part. But since these are semicircles, the area of a semicircle is 1/2 pi r squared. And again, this is going to be dx because the 0 and the pi are x limits. We're perpendicular to the x-axis. You might think that the radius is this 3 rad sine of x, but think about what that was. That's this piece right here. That would be the diameter of the semicircle, or the diameter of a circle. The radius is going to be 3/2 rad sine x, so you have to be careful. All right, let's clear some things out. This is a pi over 2, which is a number. I will kick the pi over 2 out. Once we square this, 3 halves times 3 halves is 9/4. I'm also going to kick the 9/4 out. And when I square the square root, it's just going to become sine of x. So this is going to be delightful. Here, let's see what we have. We're going to integrate from 0 to pi. I kicked out a pi over 2, 1/2 pi. I have also removed a 9/4. Again, that's 3 halves squared. So I'm going to have a 9 pi over 8 out front. And then this part, radical sine of x, being squared, is just sine of x dx. And my friends, I don't need a calculator for this. I can do this on my own. 9 pi over 8 out front. The integral of sine is negative cosine of x. But I don't want to deal with the negative, so I'm going to pull it out front as well. And we're going to integrate from 0 to pi. The pi gets to go first. Cosine of pi, that's -1. Minus, first fundamental theorem here. Cosine of 0, that's 1. So that bracket will be -2, and -9 pi over 8 times -2. Negative times negative, thankfully, is positive, because clearly there's positive volume here. It's going to be 9 pi over 4 cubic units. And there we have it. All right, one more of these. I kept the same base, the same lake, if you will, the 3 rad sine of x, but instead of semicircles popping up, now the cross sections are going to be rectangles. And they're not just any old rectangles, they're rectangles where their heights are 3 times as long as their bases are. All right, I think I'm going to make a picture of one of the cross sections. So I'm just going to grab one of these rectangles, it's like a sheet of glass or whatever, and pull it out, flip it sideways, and take a look at it. And this is what I would see. The bottom is still going to be 3 rad sine of x. The height, however, being triple that length, will be 9 rad sine of x. When you take the cross-sectional area of this rectangle, 9 times 3 is 27. The square root of sine times the square root of sine is just regular sine of x. And that 27 sine of x is what we're going to integrate, throw a dx on it, and we're going to integrate it from 0 to pi. That'll give us the volume. We'll kick the 27 out. Let's come up here, 27. Again, we saw that the integral of sine of x is negative cos, so here's the negative, here's the cos. It's going to be an instant replay of the other part, going from 0 to pi. I already know that this is going to be a -2 inside, but in it goes. Cosine of pi minus cosine of 0. So we have -2 times -27. This thing is going to have a volume of 54 cubic units. That's 27 times 2. I think we'll take a break for now from cross sections. We'll come back and do the second day of volumes by cross sections. See you then.